Good afternoon. We're going to take notes on section 7.7. And the first section of notes are going to be a review of how to do basic radical math. We did a little bit of that in the pre-7.7, but we're going to review it and do a little bit more here as well. Okay, so Roman numeral 1, simplifying radicals. How do you do it? Number 1, you prime factor the radicand. That would be the inside number. For every 2 of the same factor, 1 comes out. Once you've done that, you multiply all the outside scalars of the radical, and then multiply all the remaining prime factors in the radicand. So, for example, 1, to simplify negative radical 50, I need to prime factor the 50. So 50 is 5 times 10, so 5 times 2 times 5. We have 2 5s, so 1 is going to come out to the front and get multiplied by the negative. That's where we get negative 5 radical 2. So that's if you have a negative out front. Now let's try it with a 7 as the scalar. So first we're going to prime factor the radicand. 54 is 9 times 6. So 3, 3 for the 9, 3, 2 for the 6. 2 3s, 1 is going to come out and get multiplied by the 7. 7 times 3 is 21, and then you multiply what's left on the inside. 3 times 2 is 6. All right, that's basic simplifying. Okay, part B, how to rationalize a radical fraction. Okay, number 1, decide if it needs to be rationalized or divided. It's the same process. And you ask yourself, is there a radical in the denominator, which is the bottom? If the answer is yes, you need to rationalize it. The way you do that is you multiply the top and bottom of the fraction by the bottom radical. So you'll always be multiplying by a radical over itself. Why? Because that equals 1, and we don't want to change the value of the number, just its form. So now that you've done that, you simplify both the top and the bottom and cancel or reduce any possible factors of the outside scalar. So there is a refactor part of this process at the end because you have new numbers that could possibly reduce. All right, let's do an example. 2 over radical 27. So we want to multiply the bottom by radical 27, which means we multiply the top by the same thing, radical 27. So on the top, we have 2 radical 27. On the bottom, the two 27s get combined in the radical, and because there are 2 of them, 1 of them comes out. So that gives me a 27 on the bottom and a 2 radical 27 on the top. Now that we have a 27 on the top, let's factor that one as well. 27 is 9 times 3, so 3, 3, 3. 2 3s, 1 comes out and gets multiplied by the 2. Now this is where you can multiply 3 times 2, but if you realize that 3 is a factor of 27, you know there's some refactoring we need to do. So I'm just going to leave the top 3 times 2, radical 3, and 27 is 9 times 3, or 3, 3, 3. So our scalar 3's do divide out, and our answer is 2 radical 3 over 9. All right, example 2. We have a radical 14 on the bottom. We're not worried about the scalar 2, so we're going to multiply by square root 14 over itself. So on the top, I now have square root of 35 times 14. On the bottom, we have 2 14s combined under the same radical. So 2 14s, 1 is going to come out to the front, and 14 times 2 is 28. On the top, I'm going to prime factor this and see if anything needs to come out. So 35 is 5 times 7. 14 is 7 times 2. There are 2 7s, so 1 is going to need to come to the front. Now I can tell that 7 and 28 both are divisible by 7. So I'm going to leave the 7, square root 10, and 28 is 7 times 4. Divide out the 7s, and you have radical 10 over 4 as your final answer. All right, that is rationalizing. Now let's review basic algebra operations. Multiplying. For any two radicals, you can multiply scalar to scalar, radicand to radicand. So in this example, they're both square roots, and for multiplying, it doesn't matter that one is a square root 10 and one of them is a square root 15. That's irrelevant. We're going to multiply the scalars, so 5 times negative 3 in the front, and we're going to multiply the radicands, which is 10 times 15. 5 times negative 3 is negative 15. I'm going to prime factor the inside. I wrote radicand with a T here, sorry, it's radicand. So 10 is 2 times 5, 15 is 5 times 3. 2 5s, 1 comes out to the front. 5 times negative 15 is negative 75, and I'm left with 2 times 3 on the inside, which is 6. So negative 75 radical 6. Okay, when you divide, we've already covered that in part B. Dividing is the same thing as doing the process to rationalize the fraction. That's the same thing as division. Okay, third property is adding and subtracting. Adding and subtracting is the most picky because the radicands must match to add or subtract. They cannot be different. So, for example, in this form, I have a radical 12 and a radical 27. They're different. I can't subtract them. But it is possible for me to simplify them, and maybe what's left will match. So let's see. 12 is 4 times 3, or 2, 2, 3. 27 is 9 times 3, or 3, 3, 3. So for the 12, 2 2s, 1 comes out to the front. For the 27, 2 3s, 1 comes out to the front. I now have 4 radical 3 minus 24 radical 3. And they actually do match. So now I can put them together. 4 minus 24 is negative 20 radical 3. All right, flip the page. All right, practice simplifying. We kind of did that already on the pre-7.7, so we're actually going to skip this part. We've already done it and done our practice. We're going to go to formulas for the geometric mean. Okay, geometric mean. Okay, given a proportion, A times M or A colon M equals M colon B, the mean of the function are the two inside values. That is your mean. The outside values, if you remember, are called the extremes. That's colon form. In fraction form, A over M equals M over B. The means are the M's. Okay, so the geometric mean of this equation is M. Means are in the middle. Extremes are the ends of the expression. So in this case, the ends would be A and B. Okay, so here's an example. Solve for the mean of the equation. Okay, so we're going to solve this. Let's get a common denominator first. So this one needs an x. We multiply by x over x. This one needs a 6. We multiply by 6 over 6. Of course, now that the bottoms match, we can cancel them out. And we have 42 equals x squared. To solve for x, we need to take a square root of both sides. So square root of 42, let's see, it's 6 times 7. 2 times 3 times 7. So none of that simplifies, which means 42 stays. And x squared is x times x. So 2 x's, 1 comes out. It is positive and negative. And radical 42 stays the same. So to get your x's, we have positive x equals radical 42 and negative x equals radical 42. The left one's the easiest one to solve for. X equals square root 42. The right one you can multiply or divide by a negative 1. A negative divided by a negative is a positive x, and that equals negative square root of 42. Notice the negative interacts with the scalar, not the radicand. The plus and minus, just to emphasize, the plus and minus comes from the x, not the 42. We already know what 42 is. It's 2 and 3 and 7. They're all positive. It's x that we don't know. And the mystery about x is that if it's a positive x times a positive x, we get a positive x squared. But if it's a negative x times a negative x, if x is negative, we also get a positive x squared. So it's difficult when solving because both are possible. So whenever we take a square root of an x squared, we have to use a plus minus x or absolute value of x because we don't know which of these two situations it is. Main thing is square root of 16 is not plus and minus 4 because 16 is not an x. 16 is 4 times 4, which is a positive 4. And that's a misunderstanding that a lot of students have after working with x's, is they start to think everything is plus and minus. Before we move on, if you solve this equation for m, you get the equation m equals the square root of a times b. So you can use this form to get the means or this form, depending on what you remember. I typically just go with the fractions and don't bother with the formula, but you could do it either way. All right, flip the page. Find the geometric mean with the formula. Okay, so I'm going to show you both ways. Remember that these are the means. So if we're going to solve for the mean, we're going to solve for x. So let's start there. A over x equals x over b. To solve this, we need a common denominator. So this side needs an x over x. That side needs a b over b. Bx, bx, they cancel out. We get ab equals x squared. Take a square root, and we get plus and minus x equals radical ab. Now, since when talking about means, we're talking about side lengths. Because we're talking about side lengths, we only keep the positive x. So x equals positive AB, and x equals negative AB is extraneous. So when we're working with means, only the positive number stays. And again, that's because it's talking about side lengths. And there's the formula, x equals square root of AB. So again, the geometric mean formula is the square root of a times b, whether you derive it or memorize it. Okay, number 1, give the geometric mean between 8 and 7. Okay, so I usually think means in the middle. So 8 colon m equals m colon 7. Means are in the middle, which means 8 over m equals m over 7. And you can actually just solve that equation for m. You end up with 2 radical 14. So if you can just remember means are in the middle, you're good to go. Let's do number 2. If 5 is the geometric mean of two numbers and 13 is one of the numbers, what is the other number? Okay, so means are in the middle. So I have an unknown number with 5 as the mean in the middle, and I have 13 as the other number. Those are so your extremes are x and 13. Means are in the middle. So the geometric mean is 5. Turn that into a fraction. X over 5 equals 5 over 13. There is your equation. See how easy that is? Now to get x alone, we need to multiply by the reciprocal, which is 5 over 1, which will cancel the 5's out, and we get x equals 25 over 13 as our missing number. All right, Roman numeral 3, Theorem 8.1. Doesn't have a title, unfortunately. This does have to do with altitudes, though. So just to remind you, an altitude is where you take a point over a line and you drop the point straight down to the line, which makes a perpendicular angle. That's an altitude. So this theorem says if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So looking at this triangle, given triangle ABC with altitude Cn. Okay, so this is n, and because it's an altitude, it is perpendicular. That's your altitude towards the hypotenuse. So sometimes when doing this, it's easiest if you start with the right angle and then go to the small side. So the big triangle, we're going to go CAB, 90 degree to small side to big side. That, according to this theorem, is going to be similar to the medium-sized triangle right here. So triangle, start with the 90, that would be N. Go to the little side, which is C, and then B. And those triangles are going to be similar to the little triangle here, which of course also has a right angle here. So it's triangle N, and then go to the little side, which is A, and then C. So N to A for the little one, N to C for the medium one, C to A for the big one. It can be confusing. If the drawing you're given doesn't make it obvious, small, medium, large size, then I would recommend what we call an exaggerated triangle. So you might want to draw it with a really small side, and then a tall side, and then a hypotenuse. So it's much easier small, medium, large. And then when you drop your altitude, you'll have the same situation. It'll just be easier small, medium, large, small, medium, large. Large always being the hypotenuse. So that's just a suggestion. I'm sorry, I flicked my paper aside. There we go. So exaggerated right triangle might be something helpful. Okay, write a similarity statement for the three similar triangles. Okay, so this is QR is my short side. So triangle Q from the 90 down the short side to R across the hypotenuse to P is similar to, now let's do the medium triangle. This is the medium triangle. You have a 90 degrees, and that's the short side. So triangle MQ, and then across the hypotenuse to P. And then now the third one, similar to the small one here. So there's my 90, and there's my short side. So M across the short side to R across the hypotenuse to Q. That's your similarity statement. All right, flip the page. corollaries to 8.1. Remember, a corollary is a theorem that's so close it's not really considered a separate theorem, more like an add-on or an extension. This says when the altitude is drawn to the hypotenuse of a right triangle. Now that's exactly how the original one started, and here's where it's different. Then the length of the altitude in specific is the geometric mean between the segments of the hypotenuse. What does that mean? Okay, this is triangle ABC with angle C being 90 degrees, which means your altitude is Cn. There's the 90, altitude going to the hypotenuse. So this is saying that the length of the altitude is the geometric mean between the other segments. So altitude is the mean, and then the segments we're talking about are the small segment and the big segment. So if altitude is the mean, remember means are in the middle, segment 1 colon altitude is going to be equal to altitude colon segment 2. Altitude is the mean. So your equation is segment 1 over the altitude equals altitude over segment 2, which is exactly this formula, but this one has the letters on it. That's what the corollary says. The altitude is the geometric mean between the segments of the hypotenuse. Okay, corollary 2. When the altitude is drawn to the hypotenuse of a right triangle, so this starts out the same way, each leg is the geometric mean between the hypotenuse and the segment of the hypotenuse that is adjacent to that leg. Okay, so let's pick this apart. So first of all, we have C to N. There's our altitude, it's perpendicular. And our altitude breaks the hypotenuse into S sub 1 small segment, S sub 2 large segment. And in a right triangle, the legs are the sides that make up the 90. So we're going to call this one leg 1 and this one leg 2. So reading this again, the leg is the geometric mean. So let's pick leg 1 is the geometric mean between the hypotenuse. So that means like the entire hypotenuse. That whole thing between the hypotenuse and the segment of the hypotenuse that is adjacent. So leg 1 is the geometric mean of the hypotenuse and the segment next to that hypotenuse. So let's write that. AB is the hypotenuse, so AB and then the leg, we'll say leg 1 equals leg 1 and segment 1. So hypotenuse and the segment next to it. Making this into an equation, we have AB, the hypotenuse, over leg 1 equals leg 1 over segment 1. All right, that's one of our relationships. Okay, now we're going to do the other relationship. So the hypotenuse again. This time we're going to use segment 2 and leg 2. So the leg is the mean of the hypotenuse. Hypotenuse is AB. So AB colon leg 2 equals leg 2 colon, and this time it's the S2, that piece. So hypotenuse AB over leg 2 equals leg 2 over the segment closest to that leg, which is segment 2. And those are your two relationships that are provided by this corollary. Okay, so we're going to use this now. It says if j to r is 16, it's already labeled. E to j is 9. We want to find h to j. That would be your altitude. And then we're also supposed to find a whole bunch of other stuff. Now, RE should be easy because we just add those together. We need HE and RH. We're looking for the legs. Okay, so let's start with HJ. HJ is the altitude. So the altitude is the geometric mean of the two pieces. So our two pieces are this one, which is segment 1, and this one, which is segment 2. So if the altitude is the geometric mean, we can take segment 1 colon the altitude equals the altitude colon segment 2. So our equation is segment 1 over the altitude equals the altitude over segment 2. Now that we know what the equation is, we can fill the values in. Segment 1 is 16 over the altitude, which is hj, equals the altitude hj over segment 2, which is 9. There is our equation. Dot, dot, dot. When you solve it, you get hj equals 12. Okay, so that's the first one. We used corollary 1. Now, RE is really easy because we've got 16 plus 9. So RE is 16 plus 9, which means RE is 25. That one was really easy. Okay. So now we're going to find RH. RH, this one right here, we're going to call that leg 1. HE, we're going to call that leg 2. Okay, so we have a theorem that says that the leg is the geometric mean between the entire hypotenuse and the closest piece. So RE is the hypotenuse. So we have 25 for the hypotenuse. So let's set this up. The leg is the geometric mean. So 25 colon, we're going to say leg 1, equals leg 1 colon the nearest piece to leg 1, which is 16. All right, and let's put the numbers in. 25 over leg 1, which is RH, equals leg 1, which is RH, over 16. There is your equation. And again, you're going to solve that, and you end up with RH equals 20. Okay, last one, HE. So RH was leg 1, HE is leg 2. So let's use the theorem again. Leg 2 is the geometric mean of the entire hypotenuse and the nearest piece. So the hypotenuse is 25. We're dealing with leg 2 being the geometric mean, so it goes in the middle. And the nearest piece, which is 9. So filling in the letters, we get 25 over HE equals HE over 9. That is the equation we can solve. We end up with HE equals 15 when you get done solving that. Okay, the more times you say these corollaries to yourself, the better off you are. They can get mixed up really easily, so say them as many times as necessary so that they sound natural and memorized. That is the last page, so have a wonderful afternoon.